Mr. Kirk? We talk about the conversion nozzle flow. Actually, this equation is true for both conversion and diversion nozzle. Remember that when we talk about the mass flow rate, rho VA, that means it could be at any location, right? So this rho VA is true again for both conversion and diversion nozzle. Okay. So now this mass flow rate at the throat area, when you put ATH equal to A star for Mach equal to 1. Now again, Mach equal to 1 is only possible if you have high enough pressure in the upstream. Okay, so put that as a condition and remember that. Now, if at the throat Mach number is equal to 1, and of course, only at the throat Mach number can be equal to 1, right? So there are several conditions here. If Mach is going to be equal to 1, first of all, it can only be at the throat. Second, the pressure has to be high enough. Right? That's what we assume. So the mass flow rate is equal to this formula. Now, if you look at this, then your m dot is also equal to that. But these two will have to be equal, right? Because the A and M just have to be evaluated locally. Right? So by equating these two expressions, you will have A over A star, which is this expression. And it's only function of Mach number and gamma. Okay. So this does not matter how big the rocket or the nozzle is. It is the ratio of the cross-sectional area that is important. Okay. Now, after that, we were looking at conversion nozzle flow. Now, of course, a conversion nozzle flow, if there is a location for the Mach number to be equal to 1, will be right at the exit. Right? Because you can imagine that this is really the conversion nozzle flow. You can imagine that actually the exit is really an imaginary flow. Right? Because this is the location where your dA is equal to 0 and Mach number will be equal to 1 if the pressure ratio is large enough. So you look at the reservoir pressure being PR and the back pressure being PD. Now let's say if we are looking at P over PR, again this is the ratio. Okay? So if you look at this ratio and you say that, well, if the ratio is equal to 1, then there will be no flow and the pressure will be uniform throughout the whole nozzle. And by the time the P over P4, or let's say PP equal to P4, this ratio will be low enough that your Mach number already reaches 1 at the exit. Anything below that, it doesn't change the fact that your exit Mach number is still 1. And that means that the pressure distribution does not change any further. Right? As you lower the back pressure, or as you increase the reservoir pressure, or as you increase the ratio, or decrease the ratio above 0.4, then there will be change in pressure distribution. It's kind of like when we said in subsonic flow, the flow would adjust to an obstacle, right, on the airfoil. So here, from 1 to 4, you will know that the nozzle flow throughout the whole nozzle will be subsonic, and even the exit will be at maximum sonic condition. So the fluid or the gas in this case would adjust to the ambient pressure. So that's why you have this 1, 2, 3, and 4, and below that, there will be no difference anymore within the nozzle. The difference will be the mass flow rate, right? Because your m dot over A star is equal to PT divided by square root of RTT times this whole thing. So that means what? If I increase the reservoir pressure, I will increase the mass flow rate. There's no problem, right? And as it should be, right? Because your gas is so dense, and it goes out through the same nozzle cause the mass flow rate will have to be larger. Yes.
Back to the two formulas for mDOT, one with A and one with A star. What happens to the 1 plus attached to the gamma minus 1/2?
Which one?
In the box one, yeah, the 1 plus in that term goes away on the next equation. This creates mathematically, so what happens to it?
You plug it in Magnum, make it 1.
Going from here to here?
Yeah.
And equal to 1 and equal to A star.
You are.
M is equal to 1, so the M goes away, but there's still a 1 plus gamma minus 1/2. That's just how we're wondering what happens with 1 plus. That's just how
Yeah, you guys discuss, okay? Yeah. You seem to know, you tell me why. Okay. So, oh, you don't? Okay. Then what is your question then? If you don't, what don't you?
We just wanted to know what happens to 1 plus. So.
Where is 1 plus? Here?
You look at your mDOT equation in the box.
Yeah.
Change 1 to 2/2, and then it'll work out.
Thank you. Yeah, got it.
No, unless you got it. Let's get it straight. Where does it come from, here to there?
Yeah, we understand now.
That's equal to 1, and 1 plus is in the middle. Okay. Yes.
This is alpha plus 1/2, so I'll happen it.
Which one again? Oh, no, yeah, it's one.
You don't know what explanation? The one that's box. Okay, that's 1 plus alpha plus 1/2 times squared. And then it's just alpha plus 1/2. All the m's.
You're showing?
So my number equals 1 and then equals 1. You plug in 1 and then you common denominator and make it 2. So 2 minus 1 is 1. So that's 1 alpha plus 1.
Others? No question? You understand the question? Or is it not a question to you? Okay. This is not public trial, but what I'm trying to say is that some of it is just simple algebra. If you look at it more carefully, you should know. This M? Oh, you're all right. You mean here? So it is a question. Thank you. Okay. Yeah, thank you. Thank you for. Okay. So that means you're quite alert. That's good. It's difficult. It's so early in the morning, right? So one thing I don't quite like this early morning class is that I have to miss all the Monday night football. I watch Monday night football most of the time. I have to wake up 5 o'clock. Now, this okay now? And now, if you have sufficiently high pressure ratio, you will have Mach number equal to 1 at the exit. What is the ratio? The ratio is exactly gamma plus 1/2 to the power gamma over gamma minus 1, which is equal to 0.5283 if gamma is equal to 1.4. So that's the pressure ratio that would cause Mach number equal to 1 in the next. Questions about that? We have been talking about ratios and ratios and ratios, right? So everything in this class is nothing but ratios. Right? And ratios are very important. In many situations, we talk about ratio, right? One time we talk about Reynolds number, which is the ratio of two things, right? So fortunately, there all this. Otherwise, you have tabulated results of paper of miles and miles and miles, right? Because for every particular number, you have to make a case, right? Now you don't, because of the ratio. And this is very important in the sense that once we understand the ratio, that is important, right? So you don't need to make a case for every ratio. So what this means is that if the back pressure is vacuum, you can still have at most Mach equal to 1 at the throw. You cannot have anything faster than that. Last time there was this question. Then what happened? What happened is that the gas, right? Because this is 0.5283, and in the limiting case where Mach equal to 1 at the exit, your exit pressure, fluid pressure is equal to the back pressure, right? So that means what? If you have a vacuum in the back, but your reservoir is, let's say, 500 psi or 500 kilopascal, that means at the exit you will have 500 times at 0.5283, so 264 kilopascal. So your gas will come out of the nozzle still with high pressure and cease vacuum. So what you do, you have some expansion. Okay. So this nozzle is what we call under-expanded, because the gas is not expanded to the ambient pressure yet. Right? The pressure of the gas at the exit is higher than the pressure in the ambient. So it's under-expanded, right? In terms of expansion, it's under, right? In terms of pressure itself, it's over, right? It's higher than the ambient pressure. So exit pressure is higher than the ambient pressure, so it has not expanded enough yet, so it's under-expanded. Make sense? Okay. So once we have that done, we can you can draw a mass flow rate. Over A star, if you will. Let's talk about A throw, because A throw is now over A star, right? So here is PP over PR. It can at most be 1, right? Because 1. If you have PB higher than the PR, that means it's kind of like you are pumping the air into your tire now, right? So that's of course not an issue here because we are talking about nozzle. So when PB is equal to PR, remember this condition? That means there is no flow rate, right? So you will have a flow rate that will be increasing. Let's say this is 0.1, this is 0.2, this is 0.3, this is 0.4. So it is so interesting that you look at the increase in pressure, increase in mass flow rate as the back pressure decreases, right? And by the time we get there, this is constant.
It's slightly out of focus.
Huh?
A little bit difficult to see.
Difficult to,
See, it's a little bit out of focus.
or out of focus, okay.
Or it might be the light. The light level.
Are you able to cut out the lights in front?
That's my pen.
I don't think it's.
Yeah, okay, focus. Oh. It's adjusting.
Yeah, everything.
This is good? Okay, so this is the mass flow rate. Of course, to be more accurate, you really should put a PT in here, just to be accurate, because it's the ratio. Because remember, the mass flow rate is proportional. Earlier, as we said, the mass flow rate is proportional to PT, right? So here, this is the formula. Now, if PP is known, then of course you can simply just, for the m dot, then you have PP over PR. You can just do that. 4, 3, 2, 1. Chances are, when you are solving a numerical problem, you will already know the PP. Right? So you can calculate. However, the PP in different situations will be different. So again, it's nice just to look at the ratio. Make sense? Now this 0.5283 for gamma equal 1.4 is, after you do your problems so many times, you probably memorize that number. But it is a different value for gamma equal 1.3, for example. Okay. Did any one of you have textbook with you? Textbooks are too heavy. They have 3 problems. 1 gas dynamics. This is 2 pounds. Heat transfer like 4 pounds. Yeah, I'm talking about the electronic textbook. Okay, so for example, you look at table B2, that's on page 630. You look at M equal to 1, that ratio is 0.4854. So this will be 0.4854. Right? I think I messed up here, right? This should not be like that. This should be inverted. PP over PT, I'm sorry. This should be inverted. Now, this will be equal to 0.5457 for gamma equal to 1.3. Now these are typical values that your textbooks are talking about. And of course, this will be equal to 0.4871 if gamma is equal to 530. So this is kind of like monotonic gas. This is really 7/5. So this is diatomic. And this, of course, is anything. You can cook up with any number. Because if you think about the flow, thank you, coming out of the rockets, the gamma is really, you really have to calculate, right? Different propellants probably give you different values. Right? So these are just typical ones, so that you know. So what exactly is the number is probably not that important, right? But most likely it will be greater than 1 and less than 5/3. Right? Because gamma is CP over CP is definitely going to be greater than 1. Right? And the largest value of gamma only occurs for monatomic gas, which is like this, like 1.667. So all the values should go. For CO2, you know, if you look at your textbook, the CP over CP or CP is CO2 probably should be 1.32. So, okay. Questions about this?
Can you show us the 300?
I think I messed up twice, right? Because this value is going to be larger than 1, and your exponent will be 3.5, so this should be larger than 1. So what I will do is put a minus sign in front of it. Just to denote it. Right, makes sense, because PT is equal to P 1 plus gamma minus 1 over 2, m squared gamma minus 1. Right? So any P divided by PT should be this to the minus power. Right?
Which that was right before.
So this pressure, you can say this is equal to P star over PT. And P star is what you call critical pressure. It's just a terminology, right? You call it critical pressure. Meaning that for conversion nozzle, this one is choke. Now, let's have an example, so we will understand this better. Instead of me writing, you show it. Okay, so what is the example here? The example here is that you have air at 403 Kelvin, which is 130 degrees C, right? In 1 atmosphere, enters a conversion nozzle at 150 meters per second and expands isentropically to an exit pressure of 76 kilopascal. If the area, cross-sectional area to be monitored, the cross-sectional area of the nozzle inlet is 5 times 10 to the power minus 3 meters squared. It's about 50 centimeters squared, right? Because you can convert it. So 50 centimeters squared is equal to pi r squared. So that's about 4 centimeter diameter. Right? Find out the stagnation pressure, temperature, and enthalpy, and find out Mach number at inlet, and temperature and Mach number at cross-sectional area at exit. It all sounds pretty awful at the first sight, right? Now, since you have a conversion nozzle, first of all, you should have in mind that You should have in mind that there is an immeasurable reservoir, right? Because the problem here given is like this. But the flow will not just come in from nowhere, right? Even though it did not say, but you know there is something imaginary equivalent to its reservoir, right? This could be as innocent as when I was very young. You know, I have an older brother, about 6, 7 years older than me. Every time we went to see a movie, and I was, you know, how come these guys in the movie like even for 2 hours? Sometimes they don't eat any breakfast and lunch, right? Or they need to eat, you know. So my brother, it's not important because it's assumed they are eating, right? Because the thing is that you don't need to be told that there is such a thing, right? So we are sophisticated enough now. If the flow is entering nozzle, you can imagine that there's a reservoir somewhere, right? So you don't need to be told that way now, right? This is a really dumbed down example. Using myself as the example. You can imagine there is such a reservoir. So you think about it, it enters the nozzle, and the way I draw the nozzle flow earlier, I actually try to be somewhat accurate in the sense that if you look at this inlet, the flow did not go from 0 to some velocity right at the nozzle inlet, right? Because this is the nozzle inlet plane. You cannot say that, oh, here is velocity 0, all of a sudden here is 150 meters per second. Of course, it doesn't go like that. And if it's a reservoir, of course, it's, in a sense, it's infinite, right? We draw it this way, just as an illustration, right? So, at this point, at the inlet of the nozzle, you already have some velocity. So, for the purpose of this problem, let's just draw it like this. And you call this location 1, if you want. I'll call this location inlet, and you call this location exit. So your TI is what? 403 Kelvin. PI is equal to 1 atmosphere. And your TI is equal to what? 150 meters per second. AI at the inlet is equal to what? 5, 10 to the power minus 3 meters squared. So you are asked to find out the stagnation pressure, temperature, and so on. Right? So this is air. So gamma is equal to 1.4. C sub P is roughly equal to 1.005 joules per kilograms per Kelvin. Okay. Kilojoules. I'm sorry. 1 kilojoules. So you imagine there is a reservoir somewhere, right? That's why you were asked to calculate the stagnation pressure and so on. So the first thing is that for the problem A, your PT is equal to P any location, that's the PI, right? 1 plus gamma minus 1 over 2. MI, if you are talking about PI here, you need to talk about MI here. Gamma minus 1. So, you should be able to calculate MI. MI is equal to VI divided by gamma RTI, right? So your VI is equal to what? VI is equal to 150 divided by gamma equal to 1.4. Gas constant, 287 times 403. This will give you a number 0.373. So plug this in there. So your PT will be equal to (111.6 kilopascal). Now this one atmosphere is 101.3 kilopascal. Right? Yes.
Couldn't we just use the exit pressure and knowing that the exit Mach is 1 and get the same value?
You don't know that. You don't know. For you to be able to say that, remember the pressure ratio has to be high enough.
Okay.
But now we don't know the stagnation pressure, right? Make sense? So, now your stagnation pressure is 111.6. Now, okay, once you figure this out, you can say, let's look at the ratio, right? And from this point on, we can say that. But you cannot say the exit number is equal to 1. Now, if you look at this ratio, it goes from 111.6 to 76. You divide the 2, it's really not below 0.5283 yet. So your maximum number in this case is really not 1. Right? So, your question B, this is your question, answer to question B at the beginning. Now, what is the N, T, and exit? Right? So your C part of it, you want to look at your P at exit. PE over PT will be equal to 1. 76 kilopascal divided by 111.6 kilopascal. This gives you a value which is 0.681. So that's not below 0.5283 yet. So now you know it's not sounding at the exit. Right? So this will give you Mach and exit. Look up the table or solve the equation. Okay? This will give you one number at the exit, about 0.76. And then you can have T over TT from the table. T over TT will be 0.8964. So this will give you TE equal to 0.8964 times TT. But then what is TT? TT can be found here, right? Because it's a TI over TT and Mach equal to 0.373 is roughly equal to 0.97. So you have TT that is equal to 414.3 Kelvin. So here you have your TE roughly equal to 371 Kelvin. And you can have AE over A star times A star over AI. How do you do this? This means you have an imaginary A star here that you can refer to. Right? Because based on Mach number at the inlet equal to 0.373, you can find out AI over A star. Remember this? Right? If you don't look up the table, you put in the number. So if it's AI, that means here is MI. You put in the number, right? And your AE over A star, because now you have a Mach number at the exit, which is 0.76. You can find out that. So this is equal to AE over AI, and you can find out the number here. What you will find out is that you will have AE over A star is equal to 1.057, and this, you can say, is 1 over 1.7. Because what you find out is the AI over A star is 1.7. So now you just flip it. And that makes sense. See, at Mach number equal to 0.37, the cross-sectional area should be larger than Mach number at 0.73 or 76 in this case. So that sounds fine. So this value is less than 1, which is fine. This is equal to 0.626. So you find out AE. Just multiply that cross-sectional area by this number, and you are done. So this is a question where your A star is not in the problem, is not in the geometry given by the problem, right? So your A star is like a sea level that you cannot see from here, but you know it should be there. Make sense? Okay. Questions? Yes.
Conceptually, what exactly is a star? What does that mean?
That means if I have the sufficient pressure ratio and given this nozzle that you have, if you need to make it solid,
Where did they get the balance for?
you need to go down to that
Where did you get that
cross-sectional
1.057?
area. But now you don't have sufficient pressure ratio, right? Supposing when you go down by there, your local pressure divided by reservoir
For the
pressure
area ratio, bro.
should be equal to 0.528 gallon equal 1.4 or less. But you don't, right? You don't exactly have it because your pressure ratio is 0.681.
So we don't know that supposed to be. We don't have
Yes.
any star.
That right there, the TI over TT at 0.273
Yeah.
I don't understand how you did that.
Coming from what Mach number?
How did you get TT?
That's right here, TT. You know TI, right?
Yeah, you have TI.
TI over TT is 0.97.
How did you get that?
Isentropy relation. Or if you don't like it, or use equation. TT over NAT is equal to 1 plus gamma minus 1 over 2 m squared.
Well,
It's only these few equations, you know? After a while, you actually memorize it.
because we have Mach number.
Even if you did not try to memorize it, you
See,
will memorize
if
it.
you look at the table, it's 76, you have the area ratio.
And also, you got drilled so much with certain things. Even if you never try to memorize it, do it as a reflex.
Yeah.
Yeah, I served in Taiwan.
Yeah, if you whatever A you want.
You can drill so much because you reflex.
A star over A R.
You just know. So if you really serious with your homework and not try to look at your textbook all the time,
No,
not the one.
I don't know where the 1 over 1.7 comes from.
And in your propulsion class following the semester, all the same thing. All the similar stuff. Okay? So it's really important. If you can do this, propulsion class is simple. Because it's more applied in nature. What you are doing is you apply what you learn in this class to propulsion. Okay? Now, the next thing I want to talk about.
Professor,
Yes.
you can't assume that to be choked, right?
Huh?
You can't assume that to be choked, right? It's only has to do with back pressure and exit pressure, so.
No, it's not choking.
It's not ending
Because
with 1.
what you are having is somewhere here. Right? It's only beyond that point is choke. Meaning that your mass flow is
Yeah, when you go above
much
one to one.
Now, here's a different question.
I just didn't get that one over one thing.
If let's say I want the Mach number to be equal to 1 at the exit, given everything the same at the inlet, if you want the exit to be Mach equal to 1, what conditions would you have? So the next example is VI equal to 150 meters per second. TI again is the same, 403 Kelvin. PI equal to 1 atm. Right? But I want ME equal to 1, then this is choke, right? So the question is, what is PE? What is PE really is simple, right? PE over PT would have to be equal to 0.5283. So your PE would have to be less or equal to, then you just multiply, right? Here you already have PT, we found out earlier, right? PT is 111.6 kilopascal. So your PE has to be less than the multiplication of these two. Make sense? It would have to be 58.9 kilopascal. It has to be less than that for it to be choke.
That's because he's a listener. He's only stagnation pressure.
And once it's choke, then you can calculate all other conditions now. Now your A exit, A throw is really very stuff, right? Yeah. Okay, and now you can back calculate a lot of other things, right? Make sense to you? Okay. I think I will give you some exercise. I'll give you a quiz today.
How do you think I'm
Come on, what do you do? Very simple quiz.
Very simple, fine.
Difficult for such a large class.
All these has? What, all these has?
Can you